All right.
Hello.
Sorry, go ahead.
Hi, everyone. Thanks for attending today's brown bag session. You heard Matt there briefly. This is Jim Lochran from Earthshift. Today is going to have another great topic to go through. For those of you who have been with us on previous ones, the way we do these is we'll have Matt talk for about 45 minutes. Today we'll be talking about applying Bayesian inference to the analysis of comparative attributional LCA. So I think this is hopefully for a lot of folks on the line, this will be a very interesting topic, something that will certainly inform you in your day-to-day activities around LCA. This is the last brown bag series of 2013. So those of you who certainly attending today and have attended others, we thank you for your participation. We do have a few sessions scheduled for next year as well. We're probably going to change the timing a little bit, move them to maybe 1 or 2 per month as opposed to weekly. But really looking forward to continuing this series. If you have suggested topics or speakers, please feel free to email me, James, James, @earthshift.com. Glad to connect with those folks and bring them on board. So the way the process works is you can listen. You're in listen mode only. If you have questions, there is a questions panel over on the right-hand side of your screen on the GoToWebinar window. You can go ahead and type in your questions. I'll hold those questions until the end, and then I'll let Matt catch his breath and go ahead and ask him some questions. And we'll get through as many as we can get through in the time frame. And then if you have any other issues like can't hear or connectivity issues, there's another tab called Chat. Feel free to chat with myself, or Megan is also on the line, and we can help you with any challenges you may be having around those areas. And so with that, I'm going to go ahead and hand it off to you, Matt.
All right. Well, I appreciate everybody taking some time out of their day and attending. But I also want to take a little bit of time out of the presentation to thank Earthshift and specifically Jim for setting this up. So I do appreciate the opportunity to be able to discuss any type of data analysis type of subject matter at all. So if any of you guys know me, you know that's true. So the title of this slide is really kind of something that I took from something I presented at ICOSI earlier.
You're still there? I think we've lost your audio. See if we can get Matt back here. Hang on just a sec.
Can people hear me now?
Yes. It's a bit of a
Okay,
background,
great.
but we can hear you.
Sorry about that.
It's okay.
All right. So anyway, as I was saying, what I'll be doing is comparing and contrasting different approaches. So I'll be highlighting Bayesian mostly, but I'll be comparing it with null hypothesis statistics tests as well. You might know that better as t-tests, and you know about things like this, as well as kind of some traditional approaches to data analysis that I've seen being used in the LCA community. All right. So some of the goals that we're going to be going over is basically I want to apply analysis methods to comparative, and in this, I'm highlighting attributional because I want to make sure that it's known. At least my experience level has been mostly attributional LCA. I'm sure these techniques will work with consequential as well, but I just wanted to be very specific. And explicitly incorporate error analysis and embrace the marriage of error and magnitude to convey a message. So basically what I'm trying to say is try to step away from the point estimate and employ the error along with the point estimate so that the decision maker, your stakeholder, has the full information set from which to make decisions. One of the ways that I have come across that really treats this well is Bayesian methods, or Bayesian statistics. They inherently work with distributions. They don't rely on point estimates or report necessarily point estimates out. as a default. Distributions actually are their default. And so what I'll be doing is trying to hopefully convince you that these do have a place in LCA. And I'll be, like I said, I'll be comparing and contrasting them with not only some conventional methods, but also some null hypothesis statistical methods as well. Okay, so how did I go about doing this? First, let me lay out that there are many ways you can do it. The way I laid it out is hopefully to enhance repeatability if you guys want to go through and try this type of stuff. But there are at the end of the slide set, I'll try to point to different references that you can to which you could refer to help develop the tools or the knowledge base in order to apply in your own stuff. So the model, basically, it's a comparative LCA of two functionally equivalent parts, processes, etc. I say insert your example here because realistically, what I'm trying to get across here is the specifics of the model are irrelevant for this because it's a comparison. It doesn't matter whether I'm comparing glass bottles to plastic bottles or a turbine blade to another turbine blade. It could be anything that you want. Secondly, I used CIMA Pro Developer 733. We'll be looking specifically at the IPCC 2007 GWP, so basically global warming potential, and as well cumulative energy demand. Let's see here. So how did I go about the analysis itself? I went ahead and used the R statistical software. It's my comfort zone, so that's why I used it. With ggplot for visualization, the base packages for the standard kind of frequentist tests, and RJAGs, which is a sampler that makes the open numeric integration possible for Bayesian methods. Again, I'll go into more of these types of tools a little bit later. Okay, so I have my model, I have my comparative model, and how familiar is this plot? This plot should be very familiar, actually. This is basically the ubiquitous bar plot with a little bit of enhancements because I want to draw some points. And what do we see? Some of the pros, as you can see outlined on the right, they're succinct, they're easily readable, and people are familiar. So people tend to use them quite a bit. But if you really look at what's being presented here, you're using almost 90 or more percent of the whole area of visual area of presenting nothing, of presenting common data. So most of those bars are telling you that for most of the time, A and B are very equivalent or correlated, right? So the only real interesting point that we're trying to make here are the tops of those bars. So the difference between A and B for CED, the difference between A and B for GWP, but we're not centering our focus on that at all. And I've superimposed dots on these bars. The reason I did that is to remind us, these bars, when we show these like this, these are representing a single point data set, right? Because these points represent the substances that are aggregated to form the actual contribution of that substance to each of these impact methods, right? So after the aggregation, you're left with a single point, a single number, compared against another single point, aggregated single point, single number, on which to make a decision. You're missing half the information. So let's say we go through and we run before we go through and run a Monte Carlo, let's go dig a little bit deeper. What I showed here is that a comparison between the different products, right? So let's see here. Apologize, just a second here. What I want to dig a little bit deeper is what are the contributions to those products, right? So what are the substances involved? What are the drivers? And you can do that by doing a plot something like this, right? So right here, what I'm showing here is, note that that's a 0. right? So I'm actually magnifying the region of interest. So I did a difference between A and B, and I'm plotting the dark enclosed dots A is greater than B, and the empty circles are A is less than or equal to B. Okay, and when I see that, I can see that okay, most of those substance drivers aren't really making a difference either way. I've decorrelated those substances from the analysis, but what is standing out is natural gas, crude oil, and brown coal in this case for the instances where A is actually less than or equal to B. And then hard coal specifically for when A is greater than B. And this is for cumulative energy demand. You can go through and walk through the same type of analysis for the global warming potential. Now this is much more information rich, but again, we're looking at point estimates. We're not only looking at half the information. So, for example, what if I look at my crude oil? Now I know there's a deviation from zero. It looks like it's at about approximately a little less than 5,000 megajoules. Well, I have no evidence to suggest that I have. I mean, what's the error on that? Does it include zero? Is it really significantly different than zero? I really don't have any information telling me that that's the case. All right. So now let's move on, and let's say we've actually run a Monte Carlo analysis. Okay, so we run the Monte Carlo analysis, and what I've done here is I've just changed my shading a bit, and in dark blue is A is greater than B, light blue is A is less than or equal to B. And when I run these Monte Carlos, I actually propagate the error from my inputs all the way to my outputs. In this case, let me be very clear. I did not include error estimates for the actual characterization factors. It's only propagated up to the inventory. I just want to be clear about that. But anyway, so what do I see? So I get an estimate on my difference for both of the impacts involved, and I also get an idea that hey, they're almost 50-50 split. So given this, as opposed to my bar plot that I showed originally, I don't have a ton of confidence that there's a lot of difference between either of these processes in terms of cumulative energy demand or even global warming potential in this case. Now the rule of thumb typically in LCA is that if A is greater than B, greater than or equal to 90% of the time, so basically there's like a 90% threshold, then you can you can suggest that the results are significantly different. Now you obviously see that I have the 95% interval. We'll get into that a little bit later, but basically what that is interval is not a confidence interval. That interval is a quantile. So I set up the lower bound as the 2.5% quantile, and the upper bound as the 97.5% quantile, and those are my bounds. All right. So where are we? We're still a little confused about our results. We don't know whether we can take it for granted that the processes are different, or if we take it from the Monte Carlo that we have evidence that that we can't reject the null, or that they're the same. At this point, what we really need to do is then test whether the differences are true or not, and that enters and now that leads into what are commonly referred to as significant tests, or tests of significance for different statistics. All right. So in order to drive the point home, I'm going to let's entertain three different cases. Case one is when we have our typical set. We run the model once. We try to report it as a bar graph, and we have a one-set data point, or a one-point data set. All right. Well, in this case, I cannot evaluate this with the null hypothesis significance testing techniques that I'll get into in a bit. Why? Because it relies on historic data to inform the test itself. Now, what about case n equals 25? Yes, I can start making decisions. So we'll be looking at the n equals 25 case. In this case, this could be a process space is explored, and data was actually collected. So you actually have a fairly decent data set. Now, and then we'll also take a look at the extreme case where n equals 500 plus, and that's Monte Carlo simulation. So you're actually running your model x number, n equals 500 plus number of times with the propagated error each case, really kind of exercising your model parameters. Okay. So, what is null hypothesis significance testing? It's really one of the most common ways that we have in statistics to test whether a difference can be legitimately significant, or if the evidence, or if the data point is due just by chance, right? So it has a lot of weight because of its popularity, and it's very common. People understand them, or have at least come across them before. The problem is they're seemingly objective. They're marketed as objective, but they're seemingly objective, and I'll try to drive that point home too. So why are they called null hypothesis? So the basis of the test is you have to define a null hypothesis under which you'll be the hypothesis is exactly that you'll be testing. So for example, is A less than B, or restated, is A minus B equal to 0, right? And that's for a two-tailed thing, and I'll get that in a minute. Okay, so I'm going a lot into this one slide. Let's move on just so I can show you a little bit more in detail what's driving this. So the way a null hypothesis statistics test works is that it relies on what hopefully, if you haven't heard this before, it's called a p-value. And that's basically a probability value. So you have an existing value that you're testing. You have a null hypothesis set up that you're trying to test against. So let's say, again, A minus B is equal to 0, or restated, is the difference between A and A minus B significant? Okay. So what I'm trying to do then is I want to run my test to understand if that difference can be credibly understood as 0, or is that difference actually beyond what's credibly given as a 0 boundary? All right. So why do I have this plot here? Okay, so this is a histogram, and what I'm trying to say here is that the most likely value is right in the center. Okay, and based on whatever confidence bound that I apply to my data set, for example, let's say for LCA it's typically a 10%, so my critical value is 10, which means I'm comfortable with 90% of my data being occurring legitimately, and then 10% of my data should be cordoned off as being solely by chance, right? And the way this is, because this is a symmetric distribution, and we're looking at a difference, so A minus B is equal to 0, it could be greater than 0, but it also could be less than 0. So we have a two-tailed test. This one, upper value, and a lower value. And this boundary is defined by the critical value, which is basically whatever the upper or lower bound would calculate it out to be. That's allowable range of being equivalent to 0. All right. This region here, the shaded red region, is the actual probability that the value that I'm testing is as extreme as the critical value or more. So it's testing whether the fact that my observed value is equal to or more extreme than my critical value. And because the reason I use more extreme rather than say greater than or less than is, again, it's a two-tailed test. So it could be either greater or it could be less. All right. So the way you use this is you have a decision rule. If the p-value is within the critical region, okay, then the null hypothesis is rejected. All right. If the p-value is in this region, in between your confidence bound, then the null hypothesis cannot be rejected. Basically, there's not enough evidence to suggest that value is different from 0, and you can go on, you can, and that's what you can leave with that test. So I don't want you to think you can leave with saying, hey, I can accept the fact that this is 0. No, that's not what the test is telling you. The test is telling, all the test is telling you is that you don't have enough evidence to suggest that it is different than 0. Okay, it's a little bit different there. So what you result in is a p-values reject, or they can either reject or not reject the null. So what is that? That's a binary decision. And all that tells you is it can either be equal to it. You can either reject it, 1, or you just don't have enough evidence to suggest it's different. Okay, it doesn't tell you anything about what's the likelihood of it being close to 0 or anything like this. It doesn't give you any information about the probability of your actual value being within a certain range. Now, the other way, what is this? Okay, so actually before I go into confidence intervals, I want to step into an actual example of using a significance test with p-values. Okay, so our example is A equal to B? Okay, that's our null hypothesis. Okay, so the null hypothesis is A then minus B equal to 0. This is a two-tailed test. I'm going to use a t-test. All right, for this t-test, my assumption is that the data are independent and identically distributed. Okay, now this is something that once you start reading some of the references, or if hopefully you dust off the cobwebs and stuff, you're going to also realize that a lot of these significance tests based on frequency statistics have a ton of assumptions associated with them. So you have to make sure that those assumptions are at least loosely held so that the test is valid. All right. For this test, I'm actually set my significance level to 5%, which actually, you know what? This is a typo. Sorry, I did set this to 10, and so that means that I will end up with a 90% confidence interval. This is the general form of the t-test, right? This is the name of the actual statistic. And what you're doing is you're actually taking the difference between, the mean of group 2 minus the mean of group 1, which is basically A minus B, right? Divided, normalized by the average error. So this is basically the root mean square error. And what you have is standard deviation of the group 1, standard deviation of group 2. So it's all pooled together, all the error is. And you also have a term here called N2 and N1. Those are the actual number of samples that go into each of those groups, right? So what you can see that's driving a lot of this result is it's a ratio. So this denominator, if it gets really, really big, the value of t is going to get really, really small. And some of those things that can help really affect the number of this denominator is n, so sample size. And a little later I'm going to show you the effective sample size on your t-value. And this is one of the things that I want to drive home to this and repeat to say that some of these tests are not necessarily as objective as you think. Because what drives n? In our case, simulations. So I can make it arbitrarily very large. If I was willing to wait, I could make it n equals 1 million. So then I have 1 million sets, and this denominator is going to really, 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 it's going to adjust to the point where my t-value is always going to be in that critical region. So I'll have a p-value always significant, whether it's really true or not. And on the opposite end, when you have very, very low values of n, it's going to make that p-value arbitrarily large. And it's all dependent on when that investigator decides to either start or when the investigator decides to stop n, or let's put it in a physical experimental case, when to stop the experiment, when to stop testing, right? So it's not necessarily objective. It can be very it can be easily tweaked. All right. So for the change in the CED for the null hypothesis for the t-test, we have n equals 498 because we have minus 2 degrees of freedom because it's a two-tailed test. Our p-value is less than 5. It's actually less than 10, which in this case means that we can reject the null and we can say that it is different. So the difference between A and B is credible, and we could say that the true mean is not equal to 0. Okay, and now the p-value is almost 10, but still we are able to reject it because it's a hard, fast rule. If it's less than 10, whether it's 0.9091 or not, it's a rejectable test. There's no gradation of rejecting. It's I reject or I don't reject, period. That's it. Okay, and we can see that our confidence interval is right here, and here's our mean. Okay. So the other way that we can really assess significance is with null hypothesis tests, or with confidence intervals. Now, confidence intervals, unfortunately, have a really appealing name because they really convey the fact that I can be confident that x is going to be, or my value is going to be within here, within this within this percentage of times, and it has, and it sometimes is interpreted incorrectly by given a probability, like say x is the probability of x is going to be within this region, say 50% of the time. That you cannot get. You can't get that out of a confidence interval at all. So confidence interval defines the region of significance, okay, based on only your minimum and maximum critical points, right? So if I have a 90% confidence interval, then I have a min and max defined by my critical regions, or my critical value. And all it tells me is 90% of the time, x will fall somewhere in between that interval. Could be the middle, could be really way towards the lower end, or it could be really way towards the higher end. It cannot tell you that x is going to lie, say 60%, 40% between the upper and lower. It doesn't tell you that. All it does is tell you 90% of the time, given infinite number of samples, x is going to fall between these values. That's it. Okay. Now that's informative, but I just want to make sure that it's clear. It does not give you a probability within those bounds of x being within there. All right. Okay. So, and it also should be noted too that the interval itself is just it's a 2-point. It's defined by its range, so 2 points only. So there's not a distribution of values within those points in order to really assess probability, and we'll get into that as being a benefit from the Bayesian approach. Okay, so here I give you just kind of a standard formula for the confidence interval for the normal distribution. Right here, again, this is the standardized normal. There are different forms of the equation for confidence intervals, and they vary for the distribution. Just be cognizant of that. Again, you can see that this is driven by sample size as well. Okay. Let's see here. Okay, so yeah, again, like I said, the confidence interval is really dependent on the distribution. So make sure that if you're going to use confidence intervals, that you calculate it correctly, given the distribution with which you're working. Now, I will say this: that at least I'm not sure with CIMA Pro 8, but at least CIMA Pro 3.3, they do report a confidence interval. They actually say it's labeled confidence interval. But if you actually calculate it out, that's not what it is. It's actually the interval that I alluded to earlier, and that's the quantiles. They actually use the quantile. They don't use the confidence interval. All right. So this slide here is an example of the effect of n on my actual result. Okay. So me as an analyst, just arbitrarily setting however many number of Monte Carlo runs I want to use in my analysis. Starting with 25, because remember I can't do 1. I'm basically looking at the comparison A to B for both CED and GWP. N starting at 25, 500,000. So I can't reject 25, can't reject 500, right? And this is, sorry, and these were actually run at the 95%. So I didn't keep it consistent at 90. I apologize, but the real take-home message is, as we increased N, the rejectability of the test increases and it plateaus. So this is a visual of it. Look at the confidence interval with N equals 25. Okay, these are some things that we typically see in LCA, right? It incorporates 0. It means 0 is a plausible set of the values. Sorry, you can't reject it. Now, as we step up to 500, we're almost around that fringe, but again, the p-value wasn't quite large enough, or I'm sorry, small enough that so we still can't reject that. But now, consistently, as we increase N, both the width of those confidence intervals narrow significantly, and they're always deviating from 0. You're always going to get a positive rejection result. Okay, so I don't want to shoot down totally the significance of this type of testing. It's very, very valuable, much more valuable in my opinion for that middle set, for that 25, 50 value, something like that, where it's represents a physical data collection set, right? When you get into the simulations, when you actually have the ability to go to millions of runs, then how do you actually really test if something is significant if you know it's always going to be significant? So how do you really convey that? So anyway, with that, we're going to jump into a little bit of the Bayesian approach now. Okay, so this is just it's a really busy slide. I know I'm going to step through systematically like I did the frequentist stuff. But what I want to drive home here is note how I plot things. Now here's our lines denoting confidence intervals. Back here, well, here's a distribution and some bar plots and stuff like this. But naturally, the way a Bayesian analysis takes place, it takes into account the distributional form of the parameters you're interested in. Now again, I'm going to step into what all these things mean in a minute. It's informationally rich because you have much more than just a point value. You can assess uncertainty, and you can incorporate potentially objective and subjective errors. Now we'll get into that a little bit. I'm not going to dwell on that, but because that tends to scare people off, but it's definitely doable. And it marries prior knowledge with current data. We'll get into that too. There's definitely some cons. It's a paradigm shift, and there's a high barrier to entry to that. Right? So now not a lot of people are comfortable with saying, okay, I'm going to look at everything distributionally now. I'm going to throw away my t-sets that have been tried and true for as long as I remember studying statistics. Right? I'm asking you to at least be open to the fact that there's another way to do this, and it may be more powerful. Can definitely be computationally intensive, and this is one of the reasons why just lately, over recently, in the last 20, 30 years, that Bayesian techniques have really taken off. Now these things have been developed in the 1700s, right? But why are they so powerful now? Because we actually have the computing power to tackle the computations required. All right. So to kind of drive home the idea of what Bayes' rule is, I'm going to try to convey it in terms of a data table. And in this case, what you're looking at is what, kind of a vague idea of a inventory table. So we have substances on the as rows, we have producers as columns. It's just three producers, 3 substances, very basic, just trying to drive home some messages. All right. So what I'm going to do is introduce the concept of conditional probability. All right. So what this is saying is I want to know what is the probability of the emitted substance S1 in this case, given the fact that I'm interested in P1. All right, S1 and P1. So now I've just got this, right? Supposedly, is that really what that means or not? I'll get into that. So now what I've done in applying a addition to my full ensemble of data, the three producers, three substances. Now what I've done is I've focused the specific probability on a row and a column. All right. Let me erase this for a second so I can continue. National drawings. All right, good. All right. So now I'm going to focus on this column and this row. Excuse me if I'm going just way overboard with the drawing tools. I just think they're really cool. So I'm going to try to use them appropriately. Okay, so conditional probability say, okay, I want the probability of substance S1 conditioned on the fact that I'm only concerned about P1 in this case. So how do we understand that? Well, you can couple of that or calculate it by saying what's the probability of substance 1 and the probability of producer 1 together. That's this. This is called the joint or the conjoint probability, right? But that's just this specific case. Now notice that P1 and S1, these all have the S1, for example, S1 is emitted from P2, and P1 also has other substances being emitted. For example, in LCA terms, it's allocated over 3 different substances, right? Well, play with that with what you will, but what I'm trying to get at is this doesn't explain the whole story of the conditioned probability. What I need to do now is I have to take into account that P1 does emit other substances, so I have to divide the conjoint probability by the fact that, hey, the P1 also emits S3. So divide that out. Divide that out by the marginal probability of P1. And why is it called marginal? It's a very fancy name for the fact that back in the day, they got these sums by writing them in the margins. So they're column marginal sums and row marginal sums, and they wrote them in the margin of the paper because the table is so huge. So that's basically where that comes from. So if you do that out, so it's 0.5 conjoint, marginal, your probability of substance 1, your probability of substance 1 given probability or given producer 1 is about 40%, so 0.4. Now, let's ask the reverse question and say, okay, well, what's the probability of producer 1 emitting a substance given that it's actually substance 1, right? So what's that reverse question? Right? It's not necessarily going to be the same as the one I originally asked here. What's the probability of the emission of substance 1 given that it is producer 1? Sounds similar, but it's not necessarily the same. And if you go through the calculation, you find that it's not. However, you do find, sorry. Okay, so everything's all messed up. Sorry about that. Okay, so yeah, my animation's messed up. Apologize. What you do find is you have a common term in both probabilities. Okay, so that tells you that there's a way to actually relate this conditional probability with this conditional probability, right? And the way you do that, and I'll work it out for you, is since these are common, you can actually equate these two, all these terms, and that's all this doing. You're equating this term, this conditional by this, and this conditional term like this. If you divide out by the marginal on this side, bring it over here, you're left with this equation. This equation here is Bayes' rule. Okay, so all this is saying is the probability of S1 with respect to the fact that I'm only concerned about producer 1 can be expressed by this equation. And you can then, if you get an answer for this that's palpable, you can actually ask the reverse question and then divide out by this one, bring this over here, and ask the same question of this conditional probability. I know there's a lot of lines. We'll get into exactly what this is. All right. There's a little delay again. Sorry about this. Okay. So the anatomy of Bayes' rule. This is just a prettier form of what I showed before. Sorry, I'm drawing all over the place again. All right. What is this? This right here, the question being answered, theta are, say, the model parameters that you're interested in, and the data is what well, this is the data. It's the posterior knowledge. So it's your updated belief given the evidence you've collected, right here, the probability of the actual data itself, given the parameters that you have available, multiplied by the marginal. So the total beliefs that you have in the actual parameter set itself that you already had so it's already pre-informed data. So it's your prior belief. All right. This is where you can introduce possibly some evidence that you have based on experience, right? Based on literature values, based on one or two data points that have defined your knowledge up to this point. And then it's married to this distribution or this probability of actually observed gathered data. So you actually found it, you know it's true, you mate these two together, normalize it by the actual full data set that can be attributable, and now you have an updated set. Okay, that's the first iteration. The beauty of this is it can act as a chain. So then what happens is as you decide you gather more data or you're more informed, you can proceed through an n-length chain where this now becomes the prior knowledge because it's the knowledge you had before you are observing the data. Marry it to your more informed information, and you have an updated belief system. So basically, it's a learning model. It's a learning model. All right. So, how do we assess significance with Bayes? Well, there's a couple of ways. There's Bayes factor, and what you do, and this is just sorry for all the equations, but basically it's a ratio, and what you're doing is you're ratioing one data model for another data model, and you're going to compare those beliefs, weighted by your actual evidence, the previous evidence that you've had for Model 1 and Model 2. So you actually incorporate that prior information as well. All right, and then finally the highest density interval. So this is different. Sounds very familiar. Sounds similar to confidence intervals, but it's not. All right, in which this case where this is. This interval is the cumulative sum of all plausible probabilities of your actual of your observed value. So what I'm trying to say here is this is on this distribution, this is the cumulative sum of these probabilities. Okay, so there's actually a distribution between the values defined by the HDI. Okay, so that now I can say X is, I have 70% confidence, the probability of 70% that X is going to lie within within my HDI. Or I can say with 60% confidence that A is greater than B. You can now associate a probability to your confidence level. All right. We go a little bit faster because I'm just a little bit behind. And okay. So the summary for the Bayesian aspects are that there's Bayes factor, there's credibility density intervals, but these methods use distributions and therefore contain both magnitude and spread. So conclusions are based on the incorporation of not only the actual most plausible magnitude, but also incorporates the error in your data. Okay. Here's some references. I think I skipped over a slide, but it is contained in the set for the null hypothesis stuff too. Some references that you might want to refer for definitely some more information on background of Bayesian analysis and how to really get started. This one in particular is very, very readable. I highly recommend it. Okay. This diagram here is now going to kind of show us how we actually model our data in Bayesian terms. So again, look at they're all modeled as distributions. So for example, this could be the distribution that reflects our differences between A and B, right? Now, normal distributions are usually represented by a mean and a standard deviation parameter, right? In this case, it's precision, but don't be too scared by that. It's just a different way of expressing standard deviation. And what we do is we actually model these parameters that drive our differences by hyperparameters, right? And these hyperparameters are assigned distributions. These are your priors, okay? So these can actually be very vague. I have no information about it, or they can be they can reflect the actual information. It could be somewhat informed. All right. So done with all the background. Let's get into the actual assessment. So with the n=1 case, remember that with the null hypothesis test, we could not evaluate that test. Bayesian assessment does allow us to do that. Why? Because we mate these two together. The prior and the likelihood can be mated. Here's my my data point that I ran off of one run out of my model. Okay, and here's my vague. Look at the spread, minus e to the 12 to plus e to the 12. Right, very vague distribution. I'm just saying I don't have a lot of information about my model at all. Mate these two together. The prior dominates, and you at least can get a semi-informed idea of what your central tendency, but you're also going to incorporate the fact that you don't know a hell of a lot about what's going on with your model, right? Same thing happens with the global warming potential. Now, what if I have an informed prior? What if this bound is a little tighter? Why? I'm a pretty experienced guy. I know my processes really well. I spoke with all my process engineers. I went and sampled some data, so I have a decent idea of what what the differences should be, or what my value should be. Made that with my actual run model, and while I have a much more informed magnitude, again, reflecting my actual uncertainty. Now notice, this informed prior puts the difference from 0 quite a bit, where it actually can entertain the fact that, yeah, my CED may be different, and it may be to the point where A is less than B. And again, a similar interpretation happens with global warming potential. Now, what happens if we actually have n=25? Now, I'm not going to show the mating anymore. I'm just going to show you the posteriors. And these are the cumulative energy demand and global warming potential. And we notice that as n=25, our central tendency it's bouncing around because we're gaining more evidence. I only had one data point before, so that was the only thing that was driving it. As we become more informed, it's weighting our actual result more and more towards the true value of the difference. It's also going to shrink our error. Now, in this case, yeah, we went back to the point where it might be a little bit confusing. We may have 40% of the the probability is 40% that A will be greater than or equal to B. Or, said differently, the probability is 60% that A is less than B. Okay, whether your stakeholder is comfortable with that or not, it's at least legitimate to talk to when you to incorporate error. Okay. Same with global warming potential. Now notice, this is definitely look how different it is from 0. Okay, this is the equivalent of saying, hey, A is greater than or equal to B. That's it. All right. Now what about 500? Now, okay, on the top are means, and now I get to sample my posterior and get this a distribution of my standard deviations as well. Right? I could do that before, and that's what I was showing. And I can get an estimate not only of my best central tendency, and the probability that A is less than B, but I can also get a best estimate of my standard deviation with all the other plausible values that it may take. Same for global warming potential. Okay, these are all in form of distribution. But note, now global warming potential, this is positive, this is negative. There's a sign switch. We didn't have that before. When I showed the bar plot, I'll show this in a minute, right here. These are the static values. They were both negative. These are the original values that I showed before in the bar plot. Okay. The static value suggested that no matter what, A was going to be less than B. If we do a more robust analysis with incorporating uncertainty, we don't come at that conclusion at all. In fact, we see a sign switch and suggest that, well, maybe A is greater than B. And we can then, since it does enclose 0, we do have some skepticism, but we can quantify that skepticism in terms of probability. Same thing with CED. We get a plausible value. Here's our best estimate on our HDI. Encapsulate 0. What's the probability of this? We can calculate that. So we're able to tell our stakeholders this. We give them more informed result on which to make their decisions. Okay. Good. Plausibly different. Oh, sorry. Okay. Now, I know I went through a lot of information, and I know I got stuck on some of the meat part. I apologize for that. But I hope that I drove home the message that Bayesian inference, Bayesian statistical methods have a place in LCA. There's going to be a learning curve, but I think the learning curve is well justified given the richness of information at the output. So hopefully I was able to at least go through and introduce you, if you haven't been introduced before, what statistical methods, what the Bayesian stats are, and the methods and an application that can be used as an example. Finally, oh sorry, just one thing.
Yeah, please do.
Oh, finally, just areas of application. These are just some brainstormed areas that I thought of. You can use these, play with them, or think of your own. I think that would be that. I mean, it's just a rich playground. So with that, I'll leave on this slide so that you guys can copy it down or whatever. These are some tools that I use that are helpful in order to get started with Bayesian analysis.
Great, thanks, Matt. I think this is a bit of a flashback for me to some statistical courses I took back in school 20 plus years ago. So I appreciate that, bringing back memories, good or bad. But really interesting stuff. Let you catch your breath here. Just want to let everybody know, feel free to ask questions through the questions pane on the right, just under your GoToWebinar panel there. We have a couple queued up here. I'll answer the simple one that I can answer, which will the slides be available later? Yes, they will. We record all of these sessions, or as many as we can, and you can come back to the Earthshift website and go ahead and download the recorded version of the slides. So you get the slides and you get Matt's commentary as well, which I think is probably most helpful. One other question that came through, Matt, it's maybe a bit of a broader question, or just a chance to step back a little bit, and it's really about how do you explain this approach to your stakeholders in a way in which they'll understand it. You kind of touched upon it, I think, early on, in the sense that when you're looking at a single point, it's difficult to make it an assessment. But just wondering if you had any thoughts on kind of how you can maybe set the stage so that the stakeholder can kind of understand this concept.
Yeah, it's it's actually a really good question, and I'll be perfectly frank, it's one that I struggle with daily. And the reason I do is it's a complicated question. Basically what you're getting at is how do you convey the results of our analyses and in general, one, and then how do you convey it with more information that we're getting from the Bayesian approach? That's two. So first off, it admits that you have uncertainty, and it allows you to quantify uncertainty, in my belief, in a more robust way than do other methods that we've been playing around with in LCA. Second, rather than, say, potentially scaring off your stakeholder by throwing distributions at them or these HDI bars, etc., while I didn't have a good example, and I really should have, you can also quantify your result in terms of a probability, which you can't do right now. So I can say, hey, my result, process A versus process B, it's different, but it's not 100% different. There's some error here, but I can say it's 75% of the time, I'm willing to bet that it's different. So that gives them more leverage than it at least did before, and at least it's more informed.
Yeah, I think that's probably a great way to approach it, because everyone can kind of understand this is the best case, the least case, somewhere in the middle. And given that probability, you kind of give them that flexibility, I would say. Another question in regards to some of the tools, I think you may have had it in the slide, but are those tools open access tools, or are they tools that you have to purchase?
Great question. Okay, so there are both types, purchasable and open access. I only use open access, so all the ones that I'm listing here are open access.
Okay, great. We have time for, I think, just one more question. We're coming up to the top of the hour, and it kind of relates back into LCA in general. And I know you talked about this in comparative perspective, but does the same approach apply if you're simply looking at a single point, if you will?
Sure. Okay, so the comparison I thought was a more kind of interesting example, but you can definitely use Bayesian methods to, say, get a more robust understanding of your actual point estimate. So you run your model once, then you inform it with your prior, and you're able to now get that one idea of your CED for this process as your baseline, as your hotspot analysis, which and then you're able to apply error bounds on those. Let's see here, what else I was going to say. Additionally, though, I don't want to confuse, but I also want to make sure that it's mentioned. Another approach that you might want to note down for that case is bootstrapping techniques. Now, I know I didn't talk about it today, but at least note it down and research it yourself. It's definitely a way that you can use to help understand your process a little bit deeper.
Okay, well, great. Once again, Matt, thanks for providing the content and the time. I think this was a great discussion, great deal of content as well. And to all the folks that attended today, we had a good turnout. I want to thank you as well and wish everyone a happy holiday. And hopefully you'll come back and join us for some of the brown bags in the new year. Thank you very much. And once again, this will be posted online as well. So take care, everyone. Bye-bye.